Hi, in this video we are going to talk about metrics and evaluations in machine learning. Uh, we have already discussed the fundamentals of supervised and unsupervised learning, and we have also explored a variety of machine learning algorithms. Now, I think it's time that we dive a bit deeper into evaluating the models and selecting the parameters. In this video, we specifically are going to focus on supervised methods, regression, and classification as evaluating and selecting models when we're dealing with unsupervised learnings is often a very qualitative process. So it is not really as straightforward as we're dealing with the other sort of models in supervised learning. To evaluate the supervised models, so far we have actually split a data set into training and test. Then we built a model on the training and then we evaluated it on the test set using the score method, which is like for classification, it computes the fractions of correctly classified samples. And remember that the reason we split our data into training and test set is that we are interested in measuring how well our model generalizes to new previously unseen data. As such, we are not really interested in how well our model fit the training set, that is not useful, but rather in how well it can make predictions for the data that was not observed during the training. Now, here we are going to expand the idea of evaluation in this video. We will first introduce cross-validation, which is a more robust way to assess generalization performance, and then discuss the methods to evaluate classification and regression performance that go beyond the default measures of accuracy or are provided by the score method. We will also discuss grid search, which is an effective method for adjusting the parameters in supervised models for the best generalization performance. So in a nutshell, what is important for us is to be able to build a model that generalizes well to the unseen methods. What we have done so far has some shortcomings, which is not always a good indicators whether our model generalizes well or not, and we are trying to address that in this video. Okay, let's start by cross-validation. Cross-validation is a statistical method for evaluating generalization performance that is more stable and thorough than using a split into a training and test set, which what we sometimes do. In cross-validation, the data is instead split separately, as you can see in this picture, and multiple models are trained. The most commonly used version of cross-validation is, of course, and you may have heard about it, is k-fold cross-validation, where k is a number that we as the users specify, and that indicates to how many partitions our data is going to be divided. And it is usually 5 or 10. For example, when we are performing 5-fold cross-validation, the data is first partitioned into approximately 5 parts of equal size. This is the example that you're seeing on the screen. And that is what we call 5-fold. All these partitions are called folds. And after that, a sequence of models is trained. The first model is trained using the first fold as the test set, and the remaining folds 2 to 5 are used as a training set. So in the first row here, you see our data is divided into 5 pieces. The first piece is held out for the testing, and we train the data and the rest of it. We train the model and the rest of it. Then the model is being used, the data in folds 2 and 5, 2 to 5, and then the accuracy is evaluated for the fold 1. Then another model is built. I mean, this is a repetition process in a sense. The next one we are basically using fold 2 for the test, fold 1, 3, 4, and 5 for the training, and we continue doing that. In the end, we have collected 5 accuracy values, and the process is illustrated in the figure here. Usually the first fifth of the data is the first fold, the second fifth of the data in the second fold, and so on and so forth are going to be our test sets. And using the mean cross-validation, we can conclude that we expect the model to be around, for example, I don't know, 95% accurate on the average. So the accuracy for the model here is not the accuracy of one single training and one single model on the test set, but the average of all 5 accuracies that we have here on 5 test sets in 5 rounds of doing the cross-validation. So what are the benefits of cross-validations? There are several benefits actually to using the cross-validation instead of a single split into a training and a test set. First, remember that when doing Python, we, for example, use a train test split, which is a code that we use to perform a random split of the data. So imagine that we are lucky when randomly splitting the data and all examples that are hard to classify end up in the training set. In that case, the test set will contain only very easy examples, and our test set accuracy will be unrealistically high. Conversely, if we are unlucky, we might have randomly put all the hard to classify examples in the test set and consequently obtain an unrealistically low score. However, when we opt to use the cross-validation, then each example will be in the training set exactly once. Each example is in one of the folds, and each fold is the test set once. And therefore, the model needs to generalize as well to all of the samples in the data set for the all cross-validation scores to be high, so that the average is at the end high, so that at the end we conclude that our model is performing well. So having multiple splits of the data also provides some information about how sensitive our model is to the selection of the training data set. So this helps us understand how robust of a model we have. Another benefit of cross-validation as compared to using a single split of the data is that we use our data more effectively. When we use a traditional way of using train test split, we usually use 75% of the data for training, 25% of the data for evaluation. But when we use 5-fold cross-validation, for example, in each iteration, we can use 4/5 of the data, like 80%, to fit the model. And when using 10-fold cross-validation, we could use 90% of the data to fit the model. More data will usually end in more accurate models. But this is all not beautiful all the time. There's some disadvantages to doing the cross-validation. And the main disadvantage of cross-validation is increased computational cost. As we are now training K models instead of a single model, cross-validation will be roughly K times slower than doing a single split of data. It's also important to keep in mind that cross-validation is not a way to build a model that can be applied to new data. Cross-validation does not return a model. Of course, when we are doing it, multiple models are built internally. But the purpose of cross-validation is only, and this is important, to evaluate how well a given algorithm will generalize when trained on a specific data set. Okay, let's jump to the next topic. The fact is that splitting the dataset into k-fold by starting with the first 1/k part of the data, as you saw in the 5k-fold, is not always a good idea. It could be, let me give you an example. For example, if we have a data set that the first third of the data is class 0, the second third of the data is class 1, and the last third of the data is class 2, Then if we do a threefold class validation as data set, the first fold would only be class 0. So in the first split of the data, the test data set would only be class 0. Whereas we have trained our data set on classes 1 and 2. And as the classes in the training and test data set would be different for all three splits, the threefold cross-validation accuracy would be 0 on this data set, which is not very helpful. And we can do much better than 0 accuracy on that. As the simple k-fold strategy fails on a situation like this, it's better to use another method which is called stratified k-fold cross-validation. In a stratified class validation, we split the data such as the proportions between classes are the same in each fold as they are in the whole data set. And you can have a look at this picture. For example, if 90% of your sample belongs to class A and 10% of your samples belong to class B, then a stratified cross-validation ensures that in each fold, actually 90% of the sample will belong to class A and 10% of the sample will belong to class B. And it is usually a good idea to use a stratified k-fold cross-validation instead of k-fold cross-validation to evaluate a classifier, because it results in more reliable estimates of generalization performance. And remember, keep it in mind that in case that, for example, only 10% of the sample belongs to the class B, using the standard k-fold cross-validation, it might easily happen that one fold only contains samples of class A. And using this fold as a test would not be very informative about the overall performance of the classifier. For regression, scikit-learn package uses the standard k-fold cross-validation by default. It would be possible to try to make each fold representative of different values that regression autocrat has, but it is not commonly used strategy and would be surprising to most users. Okay. As we already discussed, we can adjust the number of folds that are used using the CV parameters. And however, scikit-learn allows for much finer control over what happens during the splitting of the data, providing a class validation splitter as a CV parameter. And this is useful for you when you're using Python. So of course, the default is k-fold cross-validation, but that doesn't mean that you need to always go with that. You could have much more control over what you're doing. For most use cases, the defaults of k-fold cross-validation for regression and a stratified k-fold for classification works well, but there are also some cases where you might want to use a different strategy. Okay, now let's see what some of these methods are. There is leave one out cross-validation, which is a frequently used cross-validation method. And you can think of it as k-fold cross-validation, where each fold is a single sample. For each split, you pick a single data point to be tested, and this can be very time-consuming, particularly for large data sets, but sometimes provides better estimates. Another one is shuffle split cross-validation, and the idea is that in shuffle split we generate a user-defined number of independent train and test splits. Samples are first shuffled and then split into the pair of train and test sets. And it is possible to control the randomness for reproducibility of the results. And this is basically done when you are using scikit-learn package by seeding the random state. Another one is cross-validation with groups, which is a very common setting for cross-validation. In this approach, there are groups in the data that are highly related. So you want to build a system to recognize, for example, emotions from pictures of faces, and you collect a data set of pictures of 100 people where each person is captured multiple times, showing various emotions. The goal is to build a classifier that can correctly identifies the emotions of the people that are not in the data set. You could use the data uh, in the way like stratified cross-validation to measure the performance of a classifier. However, it is likely that the picture of the same person will be both the training and test set. So it will be much easier for a classifier to detect emotions in a face that is part of the training set compared to a completely new face. To accurately evaluate the generalization to new faces, we must therefore ensure that the training and test sets contain images of different people. And this is when we can use uh, the, the k-fold cross-validation with groups. There are also more splitting strategy for cross-validation, and you can check it up in scikit-learn manual, but for most cases, the standard k-fold, the stratified k-fold, and group k-fold uh, will work, and these are by far the most commonly used searches. Okay, now that we know how to evaluate how well a model generalizes, we can take the next step and improve the model generalization performance by tuning its parameters. It's important to understand what the parameters mean before trying to adjust them. Finding the values of the important parameters of a model, which by that I mean the ones that provide the best generalization performance, is a tricky task, but necessary for almost all models and datasets. And because it is such a common task, there are standard methods, for example, in the scikit-learn package to help you with it. And the most commonly used method is grid search, which basically means that you try all possible combinations of the parameters of interest. We can implement a simple grid search just as for loops over two parameters, like this example. We have C and gamma, and what we are doing is that we loop over these two parameters, training and evaluating a classifier for each combination, and then decide which one is the best. The danger of overfitting the parameters and the validation set is something that is quite important here. Because, for example, we could have a result that tell us that we found a model that performs with 97% of accuracy in our dataset. However, this claim could be overly optimistic or just straight wrong. And that the reason is that we tried many different parameters and selected the one with the best accuracy on the test set. But this accuracy won't necessarily carry over to new data. Because we use the test data to adjust the parameters, we can no longer use it to assess how good the model is. This is the same reason we needed to split the data into training and the test dataset first place. And we need an independent dataset to evaluate, one that was not used to create model. And one way to resolve this problem is what we have already seen in the previous lectures. We could divide the dataset into three sets, one for training, one for validation, and one for testing the evaluation. And after selecting the best parameter using the validation set, we can rebuild the model using the parameter setting that we found, but now training on both training data and the validation data. This way we can use as much data as possible to build our model. While the method of splitting data into a training, validation, and test set that we just talked about is workable and relatively commonly used, it is quite sensitive to how exactly the data is split. For a better estimate of the generalization performance, instead of using a single split into training and validation set, we can actually use cross-validation to evaluate the performance of each parameter combination. To evaluate accuracy of the model with a particular setting of parameters, we can use five-fold, for example, cross-validation. Then we need to train 5 times the number of everything, which will be a large number of models that we need to train. And as you can imagine, the main downside of this is that it takes a huge time to train all these models. The visualization you see here, and I hope you see as well because it's pretty small, shows us how best parameter setting is selected. For each parameter setting, and here you see only a subset, 5 accuracy values are computed, one for each split in the cross-validation. Then the mean validation accuracy is computed for each parameter setting, and the parameters with highest mean validation accuracy are chosen, and that is marked by a circle here. You can see the whole process of splitting the data, running the grid search, and evaluating the final parameters in this figure. It's often helpful to visualize the results of cross-validation to understand how the model generalization depends on the parameter we are searching. As grid searches are quite computationally expensive to run, often it's a good idea to start with a relatively coarse and small grid, and then we can inspect the result of the cross-validation grid search and possibly expand our search. Okay, so far we have evaluated classification performance in the previous lectures using accuracy and regression performance using R2. However, these are only 2 of the many possible ways to summarize how well a supervised model performs on a given dataset. In practice, these evaluation metrics might not be appropriate for your application, and it's important to choose the right metric when selecting between models and adjusting parameters. One thing that you should have in mind, like a motto, is that keep the end goal in mind. Now, what do I mean by that? When selecting a metric, you should always have the end goal of the machine learning application in mind. In practice, we are usually not interested in only making accurate predictions, but also in using these predictions as a part of a larger decision-making process. Before picking a machine learning metric, you should think about the high-level goal of the application. This is what we often call business metric. The consequence of choosing a particular algorithm for a machine learning application are called the business impact. Maybe the high-level goal is avoiding traffic accidents or decreasing the number of hospital admissions. It could also be, for example, getting more users for your website or having users spend more money in your shop. So when choosing a model or adjusting parameters, you should pick the model or parameter value that have the most positive influence on the business metric. Often this is hard, as assessing the business impact of a particular model might require putting it in production in real-life systems. In earlier stages of development and for adjusting parameters, it is often infeasible to put models into production just for testing purposes because of the high business or personal risks that can be involved. For example, imagine we are evaluating the pedestrian avoidance capabilities of a self-driving car by just letting it drive around without verifying it first. If your model is bad, then for sure the pedestrians will be in bad trouble. So we often need to find some surrogate evaluation procedure using an evaluation metric that is easier to compute. For example, we could test the classifying images of pedestrians against non-pedestrians and measures the accuracy. And keep in mind that this is only a surrogate and it pays off to find the closest metric to the original business goal that is feasible to evaluate. This closest metric should be used whenever possible for model evaluation and selection. And the result of this evaluation might not be a single number, and the consequence of your algorithm could be, for example, that you have 10% more customers, but each customer will spend 15% less. So in a sense, it is not as straightforward. You should have several different factors in mind. Okay, now after all this talk, let's see how we do it in reality. And we are going to first discuss the metrics for the important special case of binary classification, and then we return to the multi-class classification, and then finally regression. Binary classification is probably the most common and conceptually simple application of machine learning in practice. However, there are a number of bottlenecks, let's say, in evaluating even this simple task. So before getting a bit deeper into the alternative metrics, let's have a look at the way in which measuring accuracy might be misleading. Remember that for binary classification, we often speak of a positive class and negative class, with the understanding that the positive class is the one that we are looking for. Often, accuracy is not necessarily a good measure of predictive performance, as the number of mistakes we make does not contain all the information we are interested in. Let me give you an example. Imagine an application to screen for the early detection of cancer using an automated test. If patient will undergo additional screening or not. So here we would call a positive test, which is an indication of the cancer, the positive class, and the negative test, a negative class. We cannot assume that our model will always work perfectly, and it will make mistakes, like human beings do as well. For any application, we need to ask ourselves what the consequence of these mistakes might be in the real world. One possible mistake is that a healthy patient will be classified as positive, leading to additional testings. This leads to some cost and an inconvenience for the patient and possibly some mental distress. An incorrect positive prediction is called a false positive. The other possible mistake is that a sick patient will be classified as negative and will not receive further tests and treatment. And the undiagnosed cancer might lead to serious health issues and could even be fatal. A mistake of this kind, an incorrect negative prediction, is called a false negative. In statistics, a false positive is also known as type 1 error and false negative as type 2 error. We will stick to false negative and false positive in this lecture, as they are more explicit and easier to remember. In the cancer diagnosis example, it is clear that we want to avoid false negative as much as possible, while false positives can be viewed as more of a minor nuisance. While this is a particularly drastic example, the consequence of false positive and false negative are rarely the same. So let me give you an example. One typical example of classification, one typical problem in classification data set is that one class is much more frequent than the other. And that is what we call imbalanced data set. If we go back to the cancer example, the number of healthy people are much more than the number of people who are diagnosed with cancer. So our data set is imbalanced in the sense that we don't have necessarily enough data on the people who are actually having cancer. In reality, imbalanced data set is a norm, and it is rare that the events of interest have equal or even similar frequency in the data set. And this is what we need to keep in mind when we are assessing our model. If we use a metric to assess our model, it should definitely be able to weed out the nonsense predictions. And one of the most comprehensive ways to represent the result of evaluating binary classification is using confusion matrix. And confusion matrix, you see an example in this uh, slide. The output of a confusion matrix is typically a 2 by 2 array where the rows correspond to the true classes and the columns correspond to the predicted classes. Each entry counts how often a sample that belongs to the class corresponds to the row quotients, while the other entry tells us how many samples of one class got mistakenly classified. We can relate the entries of a confusion matrix with the terms false positive and false negative that we introduced earlier. To complete the picture, we call correctly classified samples belonging to the positive class true positives, correctly classified samples belonging to negative class true negatives, and these terms are usually abbreviated as FP, FN, TP, and TP, which are false positive, false negative, true positive, and true negative. However, inspecting the full confusion matrix is a bit difficult, and while we gained a lot of insight from looking at all aspects of the matrix, the process is quite manual and qualitative. So there are several ways to summarize the information in the confusion matrix. For example, the first one is the accuracy. We already saw one way to basically evaluate the model is that we calculate the accuracy, which can be described as the sum of true positive and true net negative over the whole number of predictions. In other words, accuracy is the number of correct predictions, true positive and true negative, divided by the number of all samples. Precision, recall, and F-score are three other metrics that we have. Precision measures how many of the samples predicted as positive are actually positive. Precision is used as a performance metric when the goal is to limit the number of false positives. As an example, imagine a model for predicting whether a new drug will be effective in treating a disease in clinical trials. And clinical trials are notoriously expensive, and a pharmaceutical company will only want to run an experiment if it is very sure that the drug will actually work. Therefore, it's important that the model does not produce many false positives. In other words, that it has a high precision. Precision is also known as positive predictive value. Recall, on the other hand, measures how many of the positive samples are captured by positive predictions. Recall is used as a performance metric when we need to identify all positive examples. That is when it is important to avoid false negative. The cancer diagnosis example that we already discussed is a good example for this. It is important to find all people that are sick, possibly including healthy patients in the prediction. Recall has another name that is called sensitivity, hit rate, or true positive rate. There is a trade-off between optimizing recall and optimizing precision. You can trivially obtain a perfect recall if you predict all samples to belong to positive class. Then there will be no false negative and no true negative either. However, predicting all samples as positive will result in many false positives, and therefore the precision will be very low. On the other hand, if you find a model that predicts only the single data point it is most sure about as positive and the rest as negative, then the precision will be perfect, but the recall will be very bad. So while precision and recall are very important measures, looking at only one of them will not provide you with the full picture. One way to summarize them is the F-score, or F measure, which is the harmonic mean of precision and recall. And you see the formula here on the display. Basically, it is 2 times precision multiplied by recall over precision plus recall. This particular variant that you see here is also called F1 score, and it takes precision and recall into account. It can be a better measure than accuracy, specifically on imbalanced binary classifications. The confusion matrix and the classification report provide a very detailed analysis of a particular set of predictions. However, the predictions themselves already threw away a lot of information that is contained in the model. When we are making classification decisions, we can actually decide on the threshold. And what do we mean by that? For example, you want to miss less than 10% of positive samples, meaning a desired recall of 90%. Then the decision depends on the application and it should be driven by business goal. Once a particular goal is set, for example, a particular recall or precision value for class, then the threshold can be set appropriately. It's always possible to set a threshold to fulfill a particular target, like 90% of recall. The hard part is to develop a model that still has reasonable precision with this threshold. If you classify everything as positive, you will have 100% recall, but your model will be useless. Setting a requirement on a classifier like 90% recall is often called setting the operating point. Fixing an operating point is often helpful in business setting. So when we are developing a new model, it's not entirely clear what the operating point will be. And for that reason, and to understand the modeling problem better, it is instructive to look at all possible thresholds and all possible traits of precision and recall at once. This is possible using a tool called precision recall curve. There is another tool that is commonly used to analyze the behavior of classifiers at different thresholds. The receiver operating characteristic curve, or ROC curve for short. Similar to the precision recall curve, the ROC curve considers all possible thresholds for a given classifier. But instead of reporting precision and recall, it shows the false positive rate against the true positive rate. Recall that the true positive rate is simply another name for recall, while the false positive rate is the fraction of the false positives out of all negative samples. You can see the formula here. For the ROC curve, the ideal curve is close to the top left. You want a classifier that produces a high recall while keeping a low false positive rate. Compared to the default threshold of 0, the curve shows that we can achieve a significantly higher recall while only increasing the FVR slightly. The point closest to the top left might be a better operating point than the one chosen by default. Again, be aware that choosing a threshold should not be done on the test set, but on a separate validation set. For this reason, it's highly recommended using AUC curve, AUC when evaluating models on an imbalanced dataset. Keep in mind, AUC does not make sure that the default threshold, though, so adjusting the decision threshold might be necessary to obtain useful classification results from a model with high AUC. Now that we have discussed evaluation of binary classifications, let's see what do we do with multiple class classifications. Basically, all metrics for multi-class classification are derived from binary classification metrics, but averaged over all classes. Accuracy for multiple class classification is again defined as a fraction of correctly classified examples. And again, when the classes are imbalanced, accuracy is not a great evaluation metrics, and The most commonly used matrix for imbalanced dataset in multi-class setting is the multi-class version of the F-score. The idea behind the multi-class F-score is to compute one binary F-score per class, with that class being the positive class and the other classes making up the negative classes. Then these per class F-scores are averaged using one of the following strategies. We could use macro averaging, compute the unweighted per class F-score. This gives equal weight to all classes, no matter what their size is. We could have weighted averaging that computes the mean of the per class F-score weighted by their support. This is what is reported in the classification report. You can also use micro averaging that computes a total number of false positives, false negatives, and true positives over all classes, and then compute precision recall and F-score using discounts. If you care about each sample equally much, it's recommended to use the micro average of F1 score, and if you care about each class equally much, it's recommended to use the macro average F1 score. Evaluation for regression can be done in similar details as I already explained for classification. For example, by analyzing over-predicting the target versus under-predicting the target. However, in most applications that I've seen, using the default R2 used in the score method of all regressors is enough. Sometimes business decisions are made on the basis of mean squared error or mean absolute error, which might give incentive to tune models using these metrics. In general, though, we have found so far that R2 to be a more intuitive metric to evaluate regression models. So to wrap it up, we discussed cross-validation, grid search, and evaluation matrix, and the cornerstone of evaluating and improving machine learning algorithms. There are 2 points that I think is worth repeating because they're so often overlooked, and the first has to do with the cross-validation. Cross-validation, or the use of a test set, allows us to evaluate a machine learning model as it will perform in future. However, if we use a test set or cross-validation to select our model or select model parameters, we use up the test data, and using the same data to evaluate how well our model will do in future will give us overly optimistic results. So that is why we need to divide into training, testing, and training, validation, and test data set. The second point is the importance of evaluation metrics or a scoring function used for model selection and model evaluation. So what I want you to keep in mind is that you should also always have the end goal of building a machine learning task in mind. So rather than randomly or based on previous experiences, choose something. First, ask your question, what is the problem that I'm solving? And how do I measure whether I have been successful in solving that problem? So that is something that you need to definitely keep in mind before choosing a metric to evaluate your model and eventually select the model. And by that, I wrap up in this video and see you in the next one.